Hello everyone. Welcome back to the daily data structures and algorithm stream. And today we are going to solve some questions, right? Um, so I'm quickly going to do something here. I need to open this. All right. So okay. I'm just trying to set everything up nicely so we can begin the stream in a few seconds. Yesterday and the other days were actually terrible days for me to stream because of how the network played out and everything. It was really annoying. So um today we are going to study something new, and also um hopefully finish the question on the threesome closest that I started the other day. Um, you know, just have an open mind that the network doesn't get interrupted again. So I usually would like to wait for like 2 minutes before I begin the stream. Just to make sure there are, a few people around. Since now I have a lot of subscribers, but anyways, so I'll just wait a few minutes before beginning. So we'll be working on queues today. I absolutely do not know anything about queues, so I'll learn about queues as well. Um, yeah, so this is what we'll cover: queues and solve this question here, which is the threesome closest. This question is also similar to the threesome question we solved before, right? This is the threesome question. Anyways, so I'll cover that and maybe solve a question on queues before I close for this session today. All right, I think I have 20 seconds before I begin, so let me just wait around a bit. So if you are here on the stream currently, thanks for coming in. Okay, somebody said, "What is this?" Well, this is, let me see. This is data structures and algorithm, right? We are solving LEETCODE questions, studying how to solve LEETCODE questions. Yes, that's what the stream is about. Okay, so my time begins now. Let's go over the question threesome closest. I will not be replying any chats now until I finish explaining this question. So, if you have any questions, you can drop them in the chat and I'll look at them later on. So, for now, let's move on to the question. So, I was trying to, okay, here you can see I wrote certain things on the board. So, I was trying to write out some things in order for me to properly explain this question. Well, anyways, the idea about the threesome closest is quite related to the threesome, which is this question here that I solved on day 68. So, if you'd like to understand the threesome question, you can go to day 68 to understand it. But anyways, so given an integer array norms of length n and an integer target, find three integers in norms such that the sum is closest to the target. Return the sum of the three integers. So sorry, let me go over that again. I just read that badly. Given an array integer, you see, given an integer array norms of length n and an integer target, find three integers in nums such that the sum is closest to target. Return the sum of the three integers. You may assume that each input would have exactly one solution. Okay, so here is some examples here. We have in example 1, our input is nums, which is an array of some integers, a few integers here. We have -1, 2, 1, and -4. And the target is equal to 1 here. So we want to return the sum of three integers that are part of nums such that the sum is the closest we can have to the target. So you can see the sum that is closest to the target is 2, right? Because -1 plus 2 plus 1 is equal to 2. So yeah, that's exactly what the question is asking us to do. So I'll go to the board here and try to explain a few things before we continue. Now, yesterday I was trying to explain with a number plane, right? I wanted to go back to like very basic stuff. The number plane is nothing complicated actually, and it has nothing to do with the question itself. It's just me trying to explain how I will work around this question. Now, first thing we need to understand is how the closeness of a number, right, to a certain number or to another number in general. So the closeness of an integer. So let me draw a plane here, right? Now this is a fake number plane. It's not going to be perfect, so I'm just going to use, so I'll draw the middle here. Let's use white color. Okay, we can use red. Yeah, you use this. So this will be 0. We'll have all negative numbers to the left, and 3, 4, sorry, 4, 5, 6, 7, and then we'll have 1, 2, 3, 4, 5, 6, 7. Now the reason why I'm drawing this number plane is for us to actually visualize how close, or how we can find the closeness between two numbers to a particular target, right? So let's say the number let's say the number -1, right, is our target. I'll put T here. Now we want to find between -1 and, you know what, let's use -2 for example. We can use -2. Now we want to find the closer integer between -4 and 2, right? -4 and 2 to this target T here, right? We want to find out which of these integers, -4, let me put my target here, this is T, between -4 and 2, right? Which one of these integers is closer to -2? Now, because this is on a smaller scale, it is easy to tell, right? But we also need a technique to finding out which one is closer, right? Now, as we can see, we visually, when you look at the number plane, -4 is closer, right? And 2 is farther from -2. But for us to calculate this for not larger numbers, right? Let's say our target is 100, 1,000, right? And we want to know which of the numbers are closer to 1,000, right? Or a larger number between two numbers, right? So how do we calculate that? How do we know which of these numbers is closer to a given target? Well, we can do that with a simple calculation. We can say for us it will be, let's calculate again. I'll use a different color. So we want negative 4 and 2, right? These are the two integers we want to find out if they are closer to this target here, which is negative 2. So for that, we can find we can subtract negative 2 from each of the values, right? And whichever one has a larger remainder or a larger result is the one that is further apart, or the one that is not closer to our particular target, in this case negative 2. So here's what we need to do, and then the subtraction is going to be a bit different. Now, one thing you would think is we can just say negative 4 minus negative 2, right? Sorry, negative 4 minus negative 2. Okay, negative 4 minus negative 2 will be negative 2. If we do 2 minus negative 2 here, like this will be equal to um, 4 here. This is 4, and this is negative 2. Now, this is correct, right? I mean, this already validates that negative 2 is less than 4, right? But in cases where we have all negative numbers, this calculation would not work. So we will then need to do something different. We then need to find the absolute values, right, of this addition that we did here, or subtraction that we did here. So for this operation, we'll find the absolute value, right? Or we can simply represent it like this. We'll find the absolute value of this subtraction. Now, again, the subtraction will return a certain value, but this time around, we will not have any negative values here. So in this case, we'll have 2 and 4, right? Again, 2 is still inferior to 4. So meaning negative 4 is closer to negative 2 than negative 2 is to than 2 is to negative 2. So yeah, so that's really one thing I wanted to point out, and this will serve as another stepping stone for us to solve this question. Okay, so the next thing to note here is that we want to find the sum of three integers in our array. So we're given the array negative 1, 2, 1, and negative 4, I think, right? Negative 1, 2, yes, and negative 4. So here is our input, and our target t, I'll call t is going to be equal to 1, right? We want to find the sum of three integers in this array such that the result, or the sum of those three integers, is closer to our target. Now, one thing you might think we'll need to do is to just sum up this, right, and then compare directly. But we want to find every possible three integers, right? Every possible three integers we can have in this array will be in two sets, right? So we can have negative 1, 2, and 1. We can have 2, 1, and negative 4, right? Those are the possible combinations we can make. So now, for efficiency reasons, right, before we get to that, we can just simply calculate, right? So we can say negative 1 plus 2 plus 1, right? This here will be equal to 2. So I'll say negative 1 plus 2 plus 1 is equal to 2, right? And the next three pairs we'll have, right, will be 2, 1, 2 plus 1 plus negative 4, right? This will be equal to 2 plus 1 is 3, so this will be negative 1, right? Now, if we go back on our number plane, right, we have a target. Our target this time around is 1, which is at this position here. And we want to find out if between negative 1 and 2, which of these numbers is closer to the t, right? So between this and that, so this is negative 1 and 2, right? Again, we can still perform the same calculation we did before in order for us to find out, right? So we can say the target is 1, right? So we can say 1 minus, this 1 here, right? Negative 1 minus 1. We'll find the absolute value of this, right? I'll just put 2 bars here. This will be equal to 2. And then we can do the same thing again. We can say 2 minus 1, again the absolute value of that, this will be equal to 1. Now we can deduct from this operation here that 2 is obviously superior to 1, which means this 2 here is closer to 1 than this negative is to this 1 here. And from the number plane, you can visualize this, right? We can see for us to move to 1, we have to move 1, 2 steps before we get to this 1 here, right? Sorry, we can do 1 and 2, right? 1, 2 steps, which is this answer here. So, and meanwhile, in this other case here, we only need to move once to get to 1, which is our target here. So that's another thing for us to note in order for us to calculate this. Now we want to do this programmatically, right? Meaning we will have to code all of this out, but we also need some form of efficiency, meaning we want to find the possible closest number to the target faster. So in order for us to do that, we need to sort the array. So we'll have to sort this array in ascending order, right? So we'll say -4 will be our first value, -1 will be the second one, and then we have 2. Now how do we efficiently again find the triplet or the 3 integers that form this with which we will calculate the closest to t, which is our target here? Now this goes back to the 3-sum question that I explained before. In 3-sum question, we use a for loop, right, to get the first number, and we use 2 pointers to get the next 2 numbers. Now why do we need 2 pointers to get the next 2 numbers? Well, this is still the reason why we have to sort the array first of all, so that the 2 pointer works efficiently. But the 2 pointers will also serve us in a way that quickly gets us to the closest number, or the number closest to the target, right? So let's say, for example, in this case, I'll say our target is so we did this and we found -1, right? Okay, so let's say our target is this one here. Okay, we can still use this example. After sorting the array, we can choose -4 as our first integer. That will be part of the 3 integers that we need to sum up, right? So after taking this -4, we can then compare, right? We can use 2 pointers. We'll point the left and right pointers at their respective positions. Now the left pointer always points to the beginning of the array, and the right pointer points to the end of the array. Now we'll move this pointer according to the result we get from every sum, right? So in this case, if we got, so we'll need to sum these 3 integers together. So this will be -4 plus -1, right, plus 2. Now this will be -5 plus 2, which is -3. Now -3 is our current sum that we got in this case. -3 is less than our target, right? Meaning we want something closer to the target. Since the array is sorted and we got a smaller number in this case, it means the value we will get closer to the target has to be in front, right? Meaning we have to shift our left pointer to the next number, to the next highest number, because the array is sorted. So we'll do that by moving the left pointer to the next number, and our next sum, right, will be -4 plus 1 plus 2, right? Plus 1 plus 2. This is -4 plus 3, which is -1. Now we got another value, which is again smaller than our target here, right? So in this case, we can't move the pointer anymore, right? Because the pointer will will be at the position where the left pointer will be at the position where the right pointer is, which is something we don't want, right? So we stop the iteration and we move to the next number. Now the first loop will help us target the first integer that will be part of the three integers that we are summing up to, compared to the target. So we'll do that again. In the next iteration, we'll take the first integer, which is this one here, -1. Our left and right pointers will point at this position, right? And then we'll calculate again. Now we'll say this time around, the left pointer will be here. So we'll have -1 plus 1 plus 2, right? -1 plus 1 plus 2. This is going to be equal to 2, right? Again, for every calculation, I'll call this total, right? Total T. For every total we calculate, or for every sum we make in every iteration, we'll perform this this calculation here to find out if the number is truly closer to the targets that we have here. And in every iteration we will change that number, right, if the number is not. So for the first iteration, obviously we didn't have any number previously, so we will need to set -3 as the current number that is closer to the target, right? And then in the next iteration, there's room for comparison this time around. Since this, I'll call this prev closer, right? Prev closer is going to be equal to 3 in the first iteration, which is good. In the second iteration, we have a -1. Sorry, -3 is, I'll set this to -3. -3, right? And in the second iteration, now this, I'll call this the second inner iteration, right? This we'll call the next one, I'll say next closest. I'll call this next closest. Next closest is going to be equal to -1, right? Now we have the chance to compare -3 to -1 to see which one of these two integers is closer to our target, right? So that's how this question is going to play out, and we will do this for every number. So in this case, -1 will take precedence, right? -1 wins in this case because -1 is closer to 1 than -3 is, right? So we can simply find out that by performing this calculation here. Again, we'll then move to the next possible sum of 3 integers. Then this time around we'll have 2, right? And then we'll compare. So our previous closer, right, will become -1. And I mean, I might change this name in code, but we'll choose a better variable name. So -3 is no longer going to be the previous closer. Now we'll have a new previous closer, which is going to be -1. So we'll change this. This is going to be the next -1, right? So -1 is here. -1 will be compared to 2, which is this one here. So between -1 and 2, which one is closer to T, which is the target here? Well, -2 is, right? 2 is closer to 2 is closer to T, which is our target, than -1 is. So I just put an X here. I'll just try to create some symbols here. So anyways, this is all we need to do, and we'll do this for every number in this array, in our input array. Now the time complexity of this solution will be O of n squared, because first of all we are iterating for every first integer in the array, right? For every first integer in the array, and then we are also using a 2-pointer method to get the remaining 2, right? So this is going to be done in O of n squared time. All right, so let's go ahead and see how we can solve this. So I will open the chat now and see if I have some questions before I implement this. Okay, so somebody say, okay, I've answered that. Study with Sachin. Yes, hello, hello, study with Sachin, if I'm pronouncing your name very well. I don't really get what is happening here, but good luck. Okay, so the what's happening here is solving data structures and algorithm questions. So um, yeah, so that's basically what we are doing here. In case you don't understand. Okay, so I guess we can move on now, right, and implement this solution. So first of all, I submitted a solution that didn't work well, which is what I thought at first. But we are going to improve on this. This did not work in for some test cases. I mean, this test case is simple enough for this solution, but I'm not handling cases where I can, you know, get the next three numbers quickly, which is you know what? Let's forget about this and implement this. Somebody has a question. David, sorry, Javed says you can use recursion. Uh, yeah, I think I'm not sure how recursion is going to work, but I've not thought about the question in terms of recursion. But anyways, we can also try that out on our own. So let's open. So this is going to be a pointer question. So I'll put it in the two pointer problem, right? And this is three sum closest, which is going to be LEETCODE 16, right? Yes, LEETCODE 16. I'll create a new file. I'll say leet dash 16. So I write out the titles like this for those who probably go on GitHub to access the uh, solutions to each one of these questions. It will be easier for you to find if you just see, oh, leet 15, then you know it is LEETCODE number 15, right? So let's do leet, and the link to the solutions is in the description below, so you can have access to it there. So leet dash 16, right? This is going to be equal to three sum closest. So I'll say 3 dash sum dash closest. Okay, so that's what we have. And let's see. So we can copy this part of the question. That's just a boilerplate or a kickstart. Um, Hello, comfort. Hello. Okay, so let's see. So first of all, I'll import this module, which is this module that we have here. And like I said, we have three things to do here. So we need to sort the array. So first of all, we'll sort the array. Sort. Now, you might be asking yourself, why do we need to sort the array? Well, the idea of sorting the array is to simply find the next pair, right? The next pair to our current first first integer quickly by using a two pointer method. So with two pointers, the array has to be sorted, and the reason why we need to use two pointers is to quickly find the three integers, right? So we need to sort array, sort the nums, and I'll just do this by saying nums dot sort, right? We don't need to keep any reference, so this nums array is sorted automatically. Now there is something we need to do, right? And this is one of the things that disturbed or caused me issues when I was trying to solve this question this way. So the first thing I did here was to take the sum of the first three numbers. Well, this works fine, right? But a a more efficient way to do this is to take, you know, the current sum. I'll call this the current. I call this current mean, right? Current minimum. I can call this current sum, right? I'll say current sum because we need to make a comparison at the end of the day, right? So we'll say current sum, or I'll call this current closest, or okay, let's say closest sum, because the first sum we get is the closest we know of, right? So this is closest sum. Now I will not set closest sum to the sum of the first three integers. Instead, I'll set closest sum to infinity, right? Now positive infinity, to be correct, because we need to get every possible number, every possible integer, right? So let's say for example, I don't know why this thing is so large. Okay, let's say for example, right, the reason why we have to use infinity is because we want to be sure that the next sum we get is less than infinity, right? And we can then set that as our current, or our current closest number, right? Or closest sum, which is this here, right? This will be changed at the end of the day. So sorry, infinity will not be our, you know, our will not be part of our result, right? So we can change that at the end of the day. So I'll say this will be float of, infinity. So inf like this, right? So when we set this like this, then we know our current closest num to our integer, our target here is infinity, right? That is what we know of. But we know at the end of the day, when we start calculating, when we start going through the array, we will get the sum of the next three integers that are possibly closer to our target than infinity is. Infinity cannot be closer to our target than any number in the array here, even if the array is composed of zeros, right? The sum of three zeros is closer to our target than infinity is. So let's do that now. So we can set this to infinity. So this I had to research uh to learn about this. So don't think I already know this. I already knew this before the question. So let's see. Print closest sum. Let's be sure we have the actual value. Now you can see this is infinity. So which is good. Right. So now is the time to begin iterating, right? So we'll say for I in range. Now we want numbers from, the beginning all the way to the end, but two numbers, right? We want to remove two numbers, so we will iterate from this point to this other number here, and leave these two other numbers out, because when we get to this point where I is at this point, we want to be able to set our left and right pointers to the remaining numbers, right? So we need space to set our left and right pointers. So which is why we need to set the iteration to stop at the length of the length of nums minus 2. Okay, so we can do that now. Then so what we need to do next is to find the current sum, right? Both before we find the current sum, we need to set the left and right pointers. So the left and right pointers will be at the next integer and the end of the array itself. So this is going to be the left and right, left, right, or we can just set this on, so left is going to be equal to I plus 1, the next integer after I, and then right is going to be equal to um right is going to be equal to, you know, the length of nums minus 1. So length of nums minus 1. Okay, now we need a second loop, right, to move the left and right pointers. So we'll say left, sorry, while the right pointer is still less than the left pointer, right? That is the condition for us to continue this integration. So we can say, okay, now while the right is sorry, while the left is less than the right, and not like this. Left pointer is always less than the right pointer, right? So right, okay. So we can say we can then say so say current, let's call it current sum, or I'll say current closest, yes, let's call this current closest, is equal to the sum of these three integers. So we'll say nums at I plus nums at right or left first, left plus right, right. This is going to be, oh, sorry, plus nums at right. Oh, come on. So that's our current sum. Now we need the calculation, right? We need to compare, we need to perform this calculation here to find out which one between which of these sum between closest and current closest and the other closest, which one of these two is closer to our target, right? So we'll say if current, so we'll say absolute, the absolute value of this sum, right? So of this operation, so current closest minus target, right, is less than current closest, sorry, absolute value of the sum between this the subtraction of closest sum and target here, right? So if this is the case, right, then our current closest, right, our current closest becomes the closest sum to our target, right? So we'll set this, we'll say current closest, sorry, closest sum becomes current closest, right? Or if that's not the case, if this is the what happened, then we can say we begin to shift our pointers, right? So if the target, right, is less than the current closest, right, then we will move the target to we'll move the left pointer, right? Oh, sorry, we'll move the right pointer. So say right plus equal, sorry, minus equal 1. We'll shift the right pointer towards the left. Else, if the target is less than, sorry, is superior to the current closest, right, then we can move the left plus equal 1 like this. Otherwise, if it's not any of these two, then it means the current sum we found is probably equal to the target. So we can just stop, we can end everything here by just returning the current closest like this, right? Otherwise, when we are done with this iteration, we can return the closest sum instead. So let's say here we are done with all of these. So we can just say, okay, so return closest sum like this. So let's test this out and see. Solution solution is going to be, let's create an instance of the solution class, and we'll say print solution dot threesome closest. We'll use the other test case. So this is -1, 2, 1, and -4, right? And then our target is 1, I think, right? So let's print this out and see if our result is going to be equal to 2. So you can see our result is 2, so we can then go ahead and test this out in LEETCODE and see if this passes all the test cases before we submit for so let's come here. I'm just trying to get rid of this one here, so we can run this here and see how it goes. So okay, all the test cases have been passed, which is really good. So we can then submit this, right? So submission time. Okay, now this solution is O of n squared, like I said, but you can see it's efficient in LEETCODE judgment, but in terms of memory it's quite slow because first of all we are sorting this array here. I don't know, this shouldn't create any more memory in space, right? Because it's still the same array, we are sorting it in place, so we are just sorting the array, we are not creating any more memory. But in the case of this closest num, I'm not sure. This is just an integer. I think spaces space is created by arrays, right? So probably because of this, not sure, but anyways, that's the solution. So I'm going to push this to GitHub and we'll move on to the next thing. So let me move this. So say git add git commit -m. This is 2 pointers, right? 2 dash pointers, 2 pointers, and this is going to be LEETCODE dash 16. Okay. Alright, so you can have access to this question in the description from this link here. I linked it already in the description below, so it's available for everyone who wants to use this solution as well. Okay, so let's move on to the next thing. The next thing I have on the list today is studying about queues, right? So we'll read a bit about queues and we'll close for today. Tomorrow I'll begin solving queues related questions and try to understand queue even more, right? So a queue data structure is a fundamental concept in computer science used for storing and managing data in specific order. It follows the principle of first in, first out, where the first element added to the queue is the first one to be removed. Queues are commonly used in various algorithms and applications for their simplicity and efficiency in managing data flow. So here's an image or an illustration of what a queue is. So queue basically has a FIFO operation, first in, first out. I would say queues are like the opposite of stacks, because stacks is first in, right, last out, right, or last in, first out. I think in terms of stacks, if you add, let's say, when you have a stack like this, and I say I add in, you know what, I'll represent the stack, with a proper visualization, right? So we'll say this is a stack, here is a stack, I'll call this a stack, right? A stack, when I add, let's say 2, 3, 4, right? Now remember very well, I added 2 first in terms of stack, right? So come on, remember very well, I added 2 first, right, in my stack here. but 2 will be the last element to be removed, right? So in terms of stack, we remove by, removing from the top, right? So we remove this will be removed first, this will then come out, and then this will then come out. But when we are adding, 2 will go in first, then 3 will go in, then 4 will go in. So this is how we operate in terms of stack. Now, here's why I said queues are the opposite of stack. If queues are, again, from the from this article here, they said queues follows the principles of first in, first out. So meaning the first item added in a queue will be the first item to be removed, right? So in this case, I will represent queues like this. I'll say this will be a queue. So instead of closing this, I'll put it like this, right? So I'll say 2, I'll represent this 2, 3, and 4, right? So the first item was 2, right? If I were to remove the first item from this queue, right, this will be 2, right? I'll remove it straight away, and then 3 follows, and then 4 comes next, right? I don't know why that was. So again, first thing, the first to be added is the first to be removed in terms of queue. I'm not going to go too much, in details with queues, because we are just it's just an introduction to queue this time around. But let's continue. What is queue in data structures, right? A queue is a linear data structure that follows the first in, first out principle. It operates like a line where elements are added at one end, which is rear, and removed from the other end front, right? Okay, that's good. So what they're trying to say is we can remove the last item we added to a queue, which is good, right? But that is not first in, first out. Basic operations of queue data structure is enqueue, right? Enqueue, which is, in other words, insert, right? Adds element to the rear of the queue, right? So when we add an element at the end of this queue, let's say we insert, when we added 4, let's imagine 4 wasn't here before, and we added 4 to the queue, we are enqueuing that element into the queue, which is good. The queue is to remove and return the element from the front of the queue. So we remove, right, and return it. Maybe we set it into a separate variable. So pick is to just see, returns the element at the front of the queue without removing it. So we just look at it. So when we pick the front of this queue, right, when we pick this queue, it means we are seeing which item is in front of the queue. Okay, so empty means check if the queue is empty, but in this case our queue is not empty. Let me quickly put this here to annotate or to indicate that this is a queue. Here is a queue. This here is a queue. Queue. Okay, the spelling of queue itself is a controversial topic, but anyways, let's move on from that. So we have full checks if the queue is full checks if the queue is full. Okay. So maybe you have a queue of a particular size, right? Let's say this queue has to have 3 items in it. So in this case, if we run the full method on this queue, it will return true because this queue is already full, right? I don't know what I'm sure the full method will return a boolean for sure because we are checking if the queue is full, right? Okay, so task scheduling. So applications of queue, task scheduling in operating system, data transfer in network communication, simulation of real world system, waiting lines. Okay, that is good. I understand this a bit. Task scheduling, maybe you're waiting for an operation to finish before the next happens, so the next operation has to wait for this current one to finish, which is good. Okay, so real world simulation, which means people waiting in lines. Yes. So when you see a queue in real world, right? The first person in front was the first person that arrived in that queue, right? So that first person gets served first or gets attended to before the next person, right? So first in, first out. Okay, so priority queues for event processing, queues for event processing. Mm, okay, I don't know what that means. Queues can be implemented in using two techniques. So I'm going to use um, this first one. Let's see, implementation of queues. Okay, basic data structures. You know what? Let's keep scrolling. I think okay, there is nothing else here. I'll leave the link to this resource in the description. So, if anyone wants to, follow the same reading material, you can use this. So I'll put this here. Q. Okay, reading resource, resource, resource. Or let's just say reading link or useful link. Let me just put useful links here. So here it is. Save. So the link has been posted, so uh you can follow it. I think I have another question. So G4 Biru says, I'm from Brazil. I don't know English, but I wanted to tell you to have good studies. Oh wow, thank you very much. That's really nice. Thank you. Thank you for coming through. Thank you for passing by. Uh, that was awesome. Okay, so um, let's see an example of queues. I'll open this and this one too to just see if the okay, so there's an implementation here, so there's no need for the second one. So how to implement a queue using an array. So to implement a queue using an array, create an array of size n and take two variables, front and rear, both of which will be initialized to 0, which means the queue is currently empty. Elements, so we have rear. Rear is the index up to which the elements are stored in the array, and front is the index of the first element in the array. Yeah, that makes sense. Now, some of the implementations of queue operations as follows. In queue and queue addition to, like, we already read this, right? I think we saw this here already. Sorry. What? So in queue and the queue peak, empty and full. So basically this just, you know okay, you know what, let me read it. Addition of an element to the queue. Adding an element will be performed after checking whether the queue is full or not. If rear is equal to size, which means the rear is already at the end, right? The index at which up to which the elements are stored in the array. So if the rear is equal to the size, then it is said to be an overflow condition as the array is full. Else it indicates else which indicates the array is not full, then store the element at index of rear, right? Meaning we have to add an item, so there's a space to add more items in the queue. We have another chat. So love the grandma. Thank you, thank you, thank you. Speak the truth. That's the truth. Yeah, thank you for coming through. Okay, so let's move on to the next one. So the queue, removal of an element from the queue. An element can be deleted when the set, when there is at least an element to delete, right? So we can't have an empty queue and then want to delete an item from that queue. It is not possible. So we have to check at least for, an availability of one item in the queue. Else, the element at the rear front. So front is already at the beginning of the array, right? So we add an item to the front. Can be deleted, but all the remaining elements have to shift to the left by one position in order for the dequeue operation to delete the second element from the left on another dequeue operation. Okay, that was mouthful, but yeah, we get it. So front gets the element from the queue at the front, right? So if the queue is not empty, display print all elements of the queue. If the queue is not empty, traverse and print all elements from the index front to rear. Okay, so here is an illustration. I think I'll have to put this here so that I can visualize this properly. Right. Let's see. Dun-dun-dun. Okay, this is big enough, I guess. Everybody can see this. Okay, so here is a visual form of queue operation. You know what? Before I continue that, let me close this. Wait a minute. Okay, so let's read this. Below is the implementation of a queue using an array. In the below code, we are initializing the front array as 0, but in general, we have to initialize it with -1. Why is that? If we assign rear as 0, right, rear will always point to the next block of the end element. In fact, rear should point to the index of the last element. Yes, that's the point. I don't know what's going on here. When we set element in queue, it will add in the end, right? That is the current rear, and then point to the rear. Okay, that I don't get. Maybe I'm not reading this well. Interesting. You know what? Let's see a code. I'm not going to use C++. Let's see. Oh, okay. So you're using a class. Okay, the queue is a class. All right. So we have self queue, which is an array. So we initialize the front and rear to 0. I thought it said -1 here. So the capacity is C, right? Which is how big we want the queue to be. So let's see what is going on here. So if self the capacity is self the rear, which means so that means we have to shift rear every time we add an item, right? Let me see the enqueue method, queue.enqueue. Okay, so is self the rear. Self the rear will be at 0, so meaning we are not there. So let's see. So append. Okay, so we shift rear every time we add an item to the queue. That's cute. Oh, rhymes. So we shift the rear every time we add an item to the queue. Now define the queue, right? It means we want to remove an item from the queue. We want to remove an item from the queue. So when we remove an item from the queue, before we remove an item from the queue, we have to know if the queue has at least one item in it, right? Before we can, perform any removal. So if self the front, right, is equal to self the rear, it means we are still in this position, right? We are still in the initial state where the queue is empty. Self the front, should I call this pointers? I don't want to guide, right, myself in terms of the terminologies to use in queues, but we know for sure that rear and the front are both pointing at specific positions or indexes. So queue So we can display a queue, right? Okay, this is simply printing all the elements in the queue. That's good. That's good. I'm not sure why they okay they ended it with an empty. Uh, well, this will print to a new line on the last item. That's good. I'd like to try this out and see what's happening. But let's move on to the next one. This is going to be queue display. There's no peak here. I mean, there's peak, right? We saw peak, empty and full, right? Well, we can implement that ourselves. Since it's an array, we can see, how do we know if a queue is empty? Well, if the rare is equal to 0, right? Or, we can simply check if the size of the queue is going to be empty. So when the length of this is 0, or rare is at index 0, it means we don't have any item in the queue. Yes, we don't have any item in the queue if rare is equal to 0, because anytime we add an item to the queue, we have to move rare by 1, right? So rare moves every time an item is added to the queue. So rare is moved by 1 every time an item is added to the queue, which is really awesome, right? So we can use that to see if the queue is empty or not. Well, there is something I think I so you might be confused by what this really means, but the point of this is in Python, when you want to run a code, you know what? Yeah, let me just explain this. So if name is equal to main, right? So when you run the code, this code in a particular uh, file, right? Let's say the file is main.py, right? If you run this code in main.py, right, and you are currently running main.py file, this all of this here will be executed. But if you are importing this code here as a module into another file, this part of the code will not be executed, but this part of the code will not be executed, but you will have access to all of this code here, right? That, or to the class, to the queue class. So you can import the queue class from main.py into another file, right? And then you can run queue in that file, right? So this is what this simply means, which is awesome, right? So I think that's all we need to look at today. I'm not going to really go deep into queues. We'll reserve tomorrow for that. Well, anyways, so here is an illustration. We have 10 being added, blah blah blah. So this is going to be front. This is going to be the rear. You can see this is empty because this is the size of our queue, right? So we know there is still more space left to add an item. So whenever we add an item to the queue, we'll shift the rear, right? We'll increase rear by 1. Whenever we remove an item, we'll shift. Whenever we remove 10, right, we'll push the rear back and re-index every item in the queue, which is really awesome. Okay, so that's it for today, and thanks to everyone that has been here. Um, I hope you learned one or two things from this stream today. So this stream has come to an end, and we will continue tomorrow.